Okay, I have started the recording. You can present it any moment.
It's 1 minute. Hi, and welcome to today's FOM. And thanks everyone who's in person the 2 days before Turkey Day. Yeah, gobble gobble. Great crowd. Today we're gonna hear information about Mars, and our presenter is Dr. Sergeyev. He did his undergrad in Moscow Institute of Physics and Technology, and then he moved over to IKI and worked with Earth and Mars, cluster and Mars, and he defended his thesis in 2022, working on hot flow anomaly at Earth and Mars. And then he joined us here at LASP in 2023, working with MAVEN and Mars. Please, Sergey.
Thank you for this wonderful presentation. So yeah, today I will be speaking about the ionosphere-magnetosheath interactions at Mars. And before narrowing down the topic to this context, I will, how shall I click the slides? Okay. I will quickly emphasize why the Mars plasma physics is important at all. So first of all, the Mars plasma system, the Mars plasma drives a significant fraction of the whole atmospheric escape. So it's about 40 to 60% according to different estimates, which is an important factor in the long-term Mars climate evolution. Secondly, the plasma physics in general studies the radiation environment, which is essential for both human and robotic exploration, if we're really looking forward to it. And continuing this topic, if we are really looking forward to expanding the Mars exploration, we shall look into things like ground-based communications, like ground-to-ground communications on Mars. And here, plasma effects can impact the radio communication, especially if we are talking about the night side of the planet. And we're talking about the low frequency range. So if we are trying to set up two radio communication stations which are connecting to each other, we will have problems at the night side. So we need to understand this phenomenon. Then plasma physics drives effects like spacecraft charging, which is important for every space exploration mission. And last but not least, it produces aurora and other visible phenomena, which can be a powerful instrument for outreach and public engagement. All right. Narrowing the topic to the ionosphere-magnetosheath interaction at Mars. So why should we study this interaction at magnetized planets? So if we compare the Martian plasma system with the terrestrial one, the fundamental difference is that the obstacle to the solar wind in the case of Earth is the Earth's magnetic field, while in the case of Mars, the obstacle is the conductive ionosphere. So this fundamental difference drives the scale of the whole system. Sorry, let me reduce the sensitivity. All right, test. Should be better. Okay, so because the fundamental obstacle to the solar wind flow is different, the curvature of the whole system is smaller. And in the case of Mars, the curvature of the Mars plasma system is comparable to the iron J radius, while in the case of Earth, it's much smaller than the iron J radius. As a result, boundaries at Earth can be well described by one or two-dimensional models because they don't have any complex three-dimensional structures, which is not applicable to Mars. So the Mars plasma environment has more interesting topology, and that's why it's cool to study it. So generalizing the Mars experience, we can extrapolate it to other unmagnetized plasma environments like Venus, comets, and other small planetary bodies. So yeah, Mars serves as a natural laboratory to study this type of interactions. So this talk will be completely focused on the MAVEN measurements, and that's why I want to quickly reiterate why MAVEN is important. So first of all, the instrumentation on board the spacecraft provides unprecedented plasma resolution at this place of the solar system, which allows us to resolve thin boundaries in the scale of order of 1 INGR radius. And I will take advantage of it in this talk. Also, it provides one of the very few continuous solar wind monitors in the solar system, and this is the best one at Mars so far. And a bunch of other advantages. I will not focus on it too strongly. Okay, so narrowing down today's topic even more, I will focus on the three distinct aspects of the boundary dynamics that drives the atmospheric escape at Mars. The first section of the talk will be focused on the steady escape driven by the constant solar wind forcing. And this effect will be seen more or less at all times. The second portion will be focused on the seasonal variations of the escape driven by the variations of the extended hydrogen corona at Mars, which has seasonal variability. We know that it is expanded during the perihelion season because of the eccentricity of the orbit of Mars. And when this corona is ionized, it produces very extensive ion cyclotron waves, which create localized electric fields in the ionosphere-magnetosheath boundary, which locally enhances the ion escape. Lastly, I will speak about the intermittent escape and disruptions of the ionosphere-magnetosheath boundary caused by the encounter with the occasional IMF discontinuities in the solar wind. So such encounters disrupt the boundary between ionospheric and magnetosheath plasma and produce burst ion outflows, which locally enhance the total ion escape rate by 1 to 9%. All right. So before I switch to specifics of the talk, I will quickly address the terms I will be using here. So for the sake of this topic, I will call the ionosphere the region which is dominated by heavy ions, and by heavy ions I mean everything that is heavier than helium. Magnetosheath I will address as the region dominated by the shocked solar wind ions with subalvenic bulk velocity, meaning that the flow is already subsonic. And also two very specific terms I will be addressing today. The first is interplanetary magnetic field clock angle, which is angle between the interplanetary magnetic field direction in the plane perpendicular to the solar wind flow. And the clock angle is the angle between this IMF vector and the imaginary vertical line. Lastly, motional electric field is the electric field produced by the motion of the solar wind magnetic field, which is just a cross product of the solar wind bulk velocity and IMF. So it is schematically presented on this sketch. So the electric field is directed perpendicularly to both to IMF and both to solar wind bulk velocities. And it creates cool features like ion plumes, which are ionospheric ions extracted from the topside ionosphere and accelerated in one particular direction. So another quick reminder. For the sake of the first topic, we will need to use the term magnetic tension. So I want to quickly address that. and how it connects to the magnetic draping at Mars. So when interplanetary magnetic field line encounters Mars, it starts to accumulate heavy planetary ions in the middle of it, meaning that due to the conservation of momentum, the central part of the magnetic field line starts to slow down. As a result, the magnetic field line curves. And this curvature stores energy in the magnetic field, which later can be released. So this is called the magnetic tension, which is fundamentally described by J cross B equation. So if we just substitute current from the third Maxwell equation and later decompose this triple cross product, we can get the two terms. The first one is addressing the magnetic pressure gradient. So this one represents a force directed outside, oppositely directed to the magnetic pressure. And the second one, this term represents the curvature of the system. So it creates another force which tends to accelerate things in the direction of the radius of curvature, in the direction of the center of curvature. So we will use this force a lot in the next section of the talk. So let me address the first topic I will raise today, which is the steady escape driven by continuous solar wind forcing. So here's the sketch of the whole system of Mars. We have the solar wind, which is falling on the planet, and it starts to flow around the planet. Then we have the electric field, motional electric field, which we addressed a couple of slides before, which create the ion plume feature seen in the positive E hemisphere. And when this ion plume gets into the shocked solar wind region, it creates cool features like mini-induced magnetospheres. So the flow of the shocked solar wind ions starts to flow around the plume ions, creating additional magnetic field draping and interacting with the plume ion population very interestingly, which we will see later in the slides. So one of the examples of such an event is presented on the left portion of the slide. So here we have proton energy time spectrogram, then we have oxygen energy time spectrogram, number densities, magnetic field total magnitude, and the X component. So we see that when the extensive population of plume ions are observed, we also see the reversal in the X component of the magnetic field sign, representing the magnetic field draping. And we see that this magnetic field draping is coinciding with the enhanced ion densities of the plume population. Here are a couple of more examples of such an event. So once again, we have full energy time ion spectrogram. Then we have the hydrogen one, O+, O2+, electron densities. Electron energy time spectrogram. Then we have number densities of particles, bulk velocities, and magnetic field. So the key features which we see on both of these examples are that we see both O+ and O2+ particles accelerated to roughly 1 kilo electron volt. So they have rather similar energies than velocities. Both these populations remain very cold, so their temperatures remain less than 20 electron volts, which is not really expected for the region of the shocked solar wind when we have typically particles heated to several electron volts temperatures. Then, yes, we have discussed that both of these populations have rather similar energies than velocities. There is an electron enhancement simultaneously with the observed populations. And importantly, the X component of magnetic field changes sign at exactly the same moment these populations are observed. And the change of sign is represented by the change of color from the red to the blue one in both cases. Okay, so for the sake of this study, I have picked up the 1 month of MAVEN observations, and I just picked up every magnetic field X component sign reversal and made a scatter plot of the whole distribution of events. And different clusters on this picture represents different phenomena happening at Mars, which reflect the magnetic field reversal. But more specifically, I picked up 28 of them. which are attributed to the plume ions interacting with the sheath region. And here are some statistics of these events. So first of all, here are the locations. And they're all located on the night side. And by the night side, I don't necessarily mean the shadow of the planet, but the region below terminator of Mars. So this is still illuminated, but it's behind the zero coordinate of the x-axis. And the arrows here indicate the velocities of the accelerated oxygen ions. And they're both directed, they're all directed tailward. Then importantly, if we look at statistics of the angle bit of magnetic field prior and after the observations of the accelerated population, we see that the angle is increasing, meaning that the magnetic field line is straightening when we're moving away from the terminator to the tail of the planet. And the straightening of the magnetic field line means the release of energy stored in the tension force we have talked about a couple of slides before. And this energy is released in the particles velocities. And second factor which talks about the particle acceleration is this plot. So if we look at the angle between the oxygen population and the plane of magnetic field reversal, this green angle, it is decreasing when we're moving further to the tail of the planet, meaning that the particles are accelerated in the plane of the rotation of the magnetic field. And an important thing is that plasma becomes more and more compressed when we're moving further to the tail. So the ratio between between hydrogen population and not vice versa. The ratio between the heavy ion population and the all plasma population is increasing, meaning that protons become more and more depleted when these structures move to the tail, and plasma inside this structure become more and more compressed. So let's look at the exact mechanism which accelerates these particles. So when we're speaking about the magnetotail of Mars, an important factor to mention is that ions and electrons behave fundamentally different in that region due to their different gyro radiuses. So while electrons have very, very tiny gyro radiuses and they effectively follow the magnetic field lines, we call them magnetized because they are moving the same direction there. The magnetic field lines are pointing. Ions, on the contrary, have gyro radiuses comparable to the scale of the whole system, meaning that they are demagnetized. So the J cross B force, the magnetic tension, actually accelerates electrons and provides the charge separation between ions and electrons, creating a whole electric field. And this electric field, in turn, provide energy to the ions. And the electron acceleration can be evidenced by looking at the three subsets of pitch angle ion energy time spectrograms. So I have three pitch angle groups here. The first pitch angles is from 0 to 60 degrees, which is almost parallel to the magnetic field line in one direction. Third group is 120 to 180, which is the opposite direction. And then we have quasi-perpendicular pitch angles, I would say, which is between 60 and 120 degrees. All right, so if we look at the central part of the spectrogram, which is inside the magnetic field reversal itself, we see that in the quasi-perpendicular pitch angle group, there is an electron enhancement, which is absent in the pitch angle group looking along the magnetic field lines, meaning that these electrons gain energy in the direction perpendicular to the magnetic field. So the magnetic field tension energy is released in the particles. Yeah. And there are a bunch of studies also studying this type of phenomenon. And another one I wanted to quickly appeal here, the study by Zhang et al. They studied also the magnetic field reversals in the magnetosheath, and they identified two types of population. One is with with the heavy ion beam, the other one is without, and they concluded that yes, the type of phenomenon coinciding with the heavy ion population are located in the plus E hemisphere, meaning that they are most likely transported to the magnetosheath region by the ion plume, by the solar wind motion or electric field. All right, so the takeaways from this section of the talk is that this mechanism, the interaction between shocked solar wind ions and the heavies, they accelerate ions rather to similar energies associated, and this acceleration is associated with the magnetic field curvature as a result of draping of shocked solar wind population around the heavies. These high densities of ionospheric ions coincide with near void of shocked solar wind protons, meaning that the shocked solar wind protons tend to fly around these heavy ion populations. And the ratio between heavies and all plasma is keeping increasing when we're moving further to the tail of Mars, and this trend persists at least to Martian radii. So this type of phenomenon represents the persistent escape mechanism, which is observed more or less every time at Mars. Second topic I will be addressing today is the seasonal escape driven by local electric field forces. And this is attributed to the variability of the Martian hydrogen corona. So the Martian orbit has quite a big eccentricity, meaning that during different times of Martian year, the distance to the sun changes a lot. And this tends the hydrogen corona to expand and contract with respect to the season. When this corona is later ionized by the solar electromagnetic radiation, these newly produced ions are picked up, generating ion cyclotron waves, which have cadence of approximately 30 seconds. And this extensive electric field creates some phenomena which we'll be addressing here. So here's a good example of the perihelion orbit segment when the MAVEN is crossing the Ionosphere-Magnetosheath boundary in the outbound direction. So it starts in the ionosphere and enters magnetosheath. And there are cool, okay, let me describe the figures. So here we have the total ion population, the energy time spectrogram. Then we have the hydrogen one, O+, O2+. Then we have electron spectrogram, number densities, and magnetic field vector and magnitude. So first of all, we also have the observations from the LPW instrument, which measures one component of electric field, which will be essentially important in the context of this study. So first of all, right in between ionosphere and magnetosheath population, we see a large electric field enhancement. And the component of electric field which we are measuring is approximately 50 millivolts per meter, which is quite a big electric field for steady plasma conditions. This electric field spike is very compact, and it is less than 20 kilometers in altitude along the spacecraft trajectory. It is observed fairly close to the subsolar point of Mars. So the solar zenith angle here, the axis on the right, is about 25 degrees. It coincides with the change of ion composition. So the blue curve here represents the relative content of protons with respect to the whole plasma density. And this parameter is changing from 0 to 1. And while it's crossing the 0.5 point, we see the electric field enhancement. Secondly, we see a lot of features accompanying the topside ionospheric heavy ion population. So the topside ionospheric population becomes heated, and these ions are transported both in backward direction to the lower altitudes and to the magnetosheath region. So the situation in the topside ionosphere is really distorted. And this whole scenery is accompanied by the 30 seconds pulsations in the magnetosheath, which are attributed to the ion cyclotron waves generated by the extended hydrogen corona. So this is a seasonal effect. So in this work, I was trying to link the observed electric field enhancement with the features in the ion spectrograms. And in order to do that, I introduced simple particle tracing simulations. So I have fixed the electric and magnetic fields. So I did not account for the variability in time. I just set them fixed. So magnetic field I took from magnetometer because we have 3 components. Electric field, I fixed the known component, which we directly measure. And I was playing around with the remaining 2. And then I put a seed ionospheric population right in between the 2 plasmas. So I defined it as O plus ions with the temperature of 1 electron volt. And I was looking how it evolves in different setups of electric field. And here are the results I got. So depending on the remaining 2 components of electric field, I could make the seed ion population either to accelerate along the boundary. It could be transported further to the magnetosheath or accelerated backwards accelerated backwards to the lower part of the ionosphere, exactly what we are seeing at the observations. So this tail of ions is pretty much the same as what the simulations show. So the interpretation of the field generation mechanism and subsequent behavior of the ion heating is that the 30 seconds pulsations in the magnetosheath, and which are represented with blue line here. So the blue line is the angle between the proton bulk velocity and the normal to the boundary between the 2 plasmas. We see that it oscillates a lot with a cadence of half a minute. So these pulsations are likely distorting the shape of the boundary itself, producing a localized Hall electric field as a result of charge separation between ions and electrons, which subsequently these electric fields subsequently heat the topside ionospheric layer and create a reservoir to the ion escape, distorting the topside ionospheric population in many directions. All right. Here's the contrast example of the similar observations, but made at the aphelion season. So when the hydrogen corona of Mars is pretty much contracted and we don't see much ion cyclotron wave activity. So all the parameters are the same except for this orbit is inbound. So MAVEN is traveling from the shocked solar wind to the ionospheric region. And in very rare occasions, I could see the enhancement in electric field between the 2 plasmas. But this specific example I picked up is the best one where I saw the largest electric field enhancement, which we can see here. And it is important to mention here that not every electric field spike which we see on the LPW instrument is necessarily a real electric field measurement, because there are lots of effects which affect this data product, including the differential charging between the 2 booms and a bunch of other phenomena. So an important feature which can be noticed here is that this spike is it lasts like several minutes in time. Not several minutes, but half a minute, but it is too long observations to be worried about. So this is probably an instrumental effect connected with the differential charging between the 2 booms. And importantly, the topside ionospheric layer is not disturbed at this spectrogram. So speaking of statistics between the aphelion and perihelion data sets, when I looked at the perihelion data set close to Sun, nearly 60% of analyzed orbits had an electric field enhancement and the associated ion dynamics, while in the aphelion data set, only 6% of the analyzed orbits exhibited features like this one, and they were not accompanied by any of the ion dynamics showed in the previous example. So the takeaways from this section of the talk is that, first of all, we looked into one example of electric field enhancement collocated with a special ion dynamics on the top side ionospheric layer. And I introduced particle tracing simulations to link the two phenomena. These things are not seen in the aphelion data set. So statistically, I conclude that the phenomenon of electric field enhancement and the associated ion dynamics is tending to happen in the perihelion season, not the aphelion one. So it creates, so this process creates an ion reservoir for escape, and it happens on a seasonal basis. Now let's switch to the third point and the last point of the talk, which is the ionosphere-magnetosheath boundary disruptions driven by the solar wind transient events. So here I will appeal more to the events called the hot flow anomalies. They are happening when the discontinuities in the magnetic field, in the solar wind magnetic field, encounter the bow shock of the planet. And under certain magnetic field configurations, it produces the reflected ion beam, which starts to interact with the incident solar wind beam. And this interaction leads in the formation of the hot core surrounded by the two compression regions on one or both sides. And most importantly, it shifts the position of the bow shock further away from the planet, as a result, reducing the pressure on the underlying regions. So the regions between ionosphere and magnetosheath can experience a rise in altitude. And because the Martian plasma system is much compact, so compact, the ionosphere ions can leak to higher altitudes and can escape to space. All right, here's an example of the event which we studied together with my REU student, Alex Cook-Politicus. He's an undergrad currently applying for grad schools. And yeah, we developed a manuscript studying a bunch of hot flow anomalies at Mars exhibiting enhanced heavy ion activity. So what we see here, the MAVEN is located beyond the nominal bow shock position. So we observe the solar wind, but this solar wind spectra is disturbed, which is collocated with the observations of the heavy ions, both O+ and O2+ ions, which also exhibit time dispersion features. We have the enhanced electron activity. The solar wind number density is decreased, which is consistent with the expectations of the hot flow anomaly core when the core is filled with rarefied plasma, which has really hot temperatures. That's why they're called hot flow anomalies. And the solar wind bulk velocity also experiences a drop here. It's not really pronounced because the scale is logarithmic, but the drop is about 50 kilometers per second, which is pretty considerable. It's a big drop when we're talking about steady solar wind conditions. And the whole event is accompanied by the magnetic field rotation, indicating the presence of the current sheet in the solar wind. Similar events can be seen more or less everywhere across the solar system, but the key difference is that unmagnetized planets don't experience, they don't exhibit the heavy ion outflow. So here's an example of my work with my previous science advisor during my PhD years. This is from cluster, so same features. We see the time-dispersed ion beam. We see the disturbed solar wind spectra, the tenuous core surrounded by two compression regions on right and left side, and the solar wind bulk velocity is decreased from 750 kilometers to 700 kilometers. Another example is also from Earth. This is one of the best examples registered so far, a paper published based on MMS measurements. So we see all the same features. A solar wind which is disrupted by some transient event, hot ion core, energy time dispersion, compression regions on the right and left side, temperatures significantly risen in the core, and the whole scenery is accompanied by the rotation in the magnetic field. So studying structures like this, using MMS, we can really look into the details of the ion dynamics. Another, I would say, exotic example is an event like this one at Jupiter. So all the features are the same. Compression regions, hot ion core, rarefied plasma in the center. And importantly, this event is 1.5 hours in duration, meaning that it is, well, it's at least several Jupiter radiuses, which is a lot. And there are speculations about what exactly influences the sizes of these events. And there are two basic scenarios which can be valid. So the first one is that the sizes of hot flow anomalies are scaling with the distance from the sun, because the gyro radius in the solar wind keeps expanding because of the weaker magnetic field magnitude. A second one is that the size of the hot flow anomaly is fundamentally connected with the curvature of the bow shock of the planet. And based on some recent statistics, we can conclude that the latter is probably more important. So the Jupiter has enormous hot flow anomalies just because its bow shock is so big. But if we are looking at the events, such events observed at the magnetized planets such as Earth, here's an example of hybrid simulations of hot flow anomalies at Earth. We see that due to the big scale of the whole system and large standoff distance between the bow shock itself and the hot flow anomaly, the hot flow anomaly are very unlikely to have any effect on the underlying plasma regions, such as magnetosphere or ionosphere, unlike Mars. So at Mars, the bow shock is located so closely to the ionosphere so that even a small disturbance at the surface of the bow shock can disturb the underlying ionospheric region and cause the extraction of the heavy ions and the subsequent escape to space. So in the paper with my RU student, we concluded that this particular event caused an additional ion escape it expanded the nominal ion escape at Mars by 9%. And he also looked at the range at several similar events, and we selected about 5 events, and the range of ion escape variation was about 1 to 9%. So it's not a big factor, but it is still persistent, and it might be even more important in the context of the early sun. So the cumulative effect of the hot flow anomalies influence on the evolution of the planet can be significant, because the early sun and the stars in general, when they are younger, they tend to rotate faster. Faster rotation of the sun means more frequent IMF changes, because the heliospheric current sheet is crossing more frequently. And the dynamo processes in the star itself are also more pronounced when the rotation is faster, meaning that the associated hot flow anomalies events can be much, much more stronger. So the cumulative effect over the evolution of the planetary system can be significant, and it still needs to be studied. So the takeaways from this section of the talk is that events such as hot flow anomalies tend to trigger additional atmospheric escape, and this atmospheric escape is representing a novel escape mechanism. It locally expands, it locally increases the total escape by 1 to 9%, and its cumulative effect may be significant given a more active ancient sun. And this type of phenomena can sporadically modify the atmospheric escape at planets. So what what I am thinking of taking my research further is that on each of the three topics, I have some ideas in mind, so where to take that. The first one, when we were talking about the steady ion escape, the steady shape of the boundary between ionosphere and magnetosheath, I see that we recently released an updated data set based on LPW measurements, which provides a very reliable densities data sets, which can be studied with focus on the influence of steady conditions on the shape of the boundary. So now we can study it in real detail. The seasonal electric field generation mechanism, which I was presenting in the second part, can be validated using the hybrid simulations, which are already available. So it can provide a more confidence to the link between the observed electric field enhancement and the ion features. And lastly, we can study the cumulative effect of hot flow anomalies on Mars system as focusing on the lifetime of the whole planet. And in order to do this, we need to look into variations of hot flow anomaly statistics over the one solar cycle, and then we can extrapolate its behavior to the younger sun. So, yeah, summing up, we have looked into three distinct phenomena. First of which is representing the steady ion escape. Then we looked into some seasonal variations of ion escape, and then we studied the phenomena providing the intermittent escape, which, yep, that's it. Thank you.
Thank you for a great talk. The questions is open to the floor. Anyone on the internet, please raise your hand if you have. Anyone questions?
Hey, good talk, Sergey. This is Erin. I have a simple question, I guess. You talked about some other places where hot flow anomalies are observed in the solar system. I had to look up cluster because I didn't know what it was, and I didn't even know what planet it was at. So my question is, I think I gathered that was Earth, and then we looked at Jupiter. Did you mention, and if you did not, is there any information about hot flow anomalies at someplace like Venus, for example?
Yes, there are a bunch of publications focusing on Venetian hot flow anomalies, and they were made by the Venus Express orbiter.
Okay.
Yeah.
Cool, thank you.
Great, thanks. I was going to ask about the hot flow anomalies also, and maybe this is my Earth bias. I was curious, one, why the scale of them is likely dependent on the scale of the planetary system, and then also if that means, has anyone tried to quantify the kind of impact of them at other planets, and is it that the smaller planets, they have larger impact?
Yeah, so the first question was about the sizes of the events with respect to the curvature of the whole system. So no, conclusive takeaways have not been made yet because it requires complex simulations, which are still to be done, I guess. But there are some speculations in the papers studying the comparative features of these events at different planets. And the general trend is that the scale of hot flow anomalies are they look to be directly proportional to the curvature of the system rather than to the distance from the sun, which is just observational data. But if we try to justify this behavior, this is probably because of the ion dynamics, because the trajectory of a single particle in the hot flow anomaly is very complex, so it's traveling back and forth of the nominal position of the bow shock. So probably the ion dynamics is different when the curvature of the system is different. The second question you asked was about, sorry, I forgot it. Net impact on the planet. Yeah, I would say that there are very few papers focusing on the ion escape associated with hot flow anomalies. So one of the papers is our papers, and the other one is from it's also a Maven paper, and they speculated that, yeah, the hot flow anomaly triggers the atmospheric escape, but they did not quantify it. And I think that's it. It's a very fresh field, I would say. Yep.
Yes, very nice talk. I'm going back to your bullet 1 there, the steady escape. So with the plume in the northern hemisphere, I would think would be dictated by Parker field that's pointing away from the sun to get the electric field to point in northward direction. Whereas if that flips to an, towards sector magnetic field, that electric field should then flip to southward. So have you studied the north-south variations of this study, the plume?
I was using for the sake of the study, I was using the reference frame, which is called MSE. So when you have the z-axis pointing in the direction of the electric field, x is pointing to the sun. And yeah, generally we see that this type of events are observed in the positive E hemisphere. We didn't really look into the ecliptic plane. Sorry, I probably didn't get your question.
Okay. Maybe I'll clarify. So it's the V cross, E is minus V cross B.
Correct.
Right, and V is from the sun.
Yeah, V is the bulk velocity of solar wind.
Right,
which is
that's pointing towards the planet.
towards the planet from the sun.
And the magnetic field is perpendicular to that. And so, I mean, you should get a flip depending on the magnetic field of the Parker field, right?
Depending on the clock angle of magnetic field. Because if magnetic field is radial, the electric field is zero.
Sure, but
the cross product is zero.
Sure, but most of the time you would have either towards or away from the sun. That's the Parker fields.
Yep.
Right. Yep. So you should get a northern plume and a southern plume, or have people
that's right. Yep.
Yeah.
It rotates.
And you have then looked at the northern versus. Yep. Have you looked at this north-south?
Yes. So we see that asymmetry.
So there's a southern plume too for those conditions, huh?
Yeah.
Should be.
So I understand the question. The thing is that when we're talking about the plume, we usually make a coordinate system conversion, and we run away from the conventional coordinate system connected with the ecliptic plane.
But that shouldn't. The solar wind doesn't care about that.
The solar wind doesn't care. It's flowing radially from the sun.
Right.
But you rotate.
Anyway, we can talk about
this
offline.
Any other? Do we have any questions? Oh, we have multiple here on the Shangxing.
Hi, this is Shani. So I think Stefan already asked one of my questions. That will be for the first step when you were talking about steady escape driven by solar wind forcing. Does it matter what coordinates you're in? Because some people use the electric field as the other axis. So my first question was about how the rotation of the electric field could contribute to this escape rate. But I think you answered that question already. The second question is, I'm very naive on the Maven environment. You showed how the magnetic field is the shape changed, so it's causing all these effects. But first question is that the draping of the magnetic field that people talk about?
So the second question is related to the steady ion escape. Is that correct? So you're talking about
yes. So you show the magnetic field line, the change of the shape. So, but the question is that the magnetic field draping effect on Mars, or is it not?
So the initial escape is provided by the electric field, and it's the ion plume. But then this population is subsequently accelerated by the interaction with the shocked solar wind plasma. That was my point. if that answers your question.
Oh, okay, good point. I think the other figure was a little bit confusing to me. Okay, cool, thanks. And then the second question is like, we don't have, well, we have a lot of flux tubes and stuff like that on Mars. Is that right?
Sorry, we have some issues with the sound. Could you repeat?
Okay. So we have flux tubes on the day side that's going along the flux tube, right? So will that contribute to what you show here? Because that's what you show here is more or less a steady state.
Yes.
But there are going to be transient changes. So how would those couple to each other? Because they work on different. I guess they work on different coordinates too.
So yeah, the draping of magnetic field at Mars happening at all times. The question is under which geometry and the orientation of interplanetary magnetic field these draping tubes are filled with the ion plume populations. So yeah, depending on the orientation of magnetic field, these mini magnetospheres, as they're called in some publications, they can either be filled or not filled with the heavy ions. Is that
okay?
The answer?
Yeah.
Okay.
Cool. That's good. Thank you so much.
Mm-hmm.
Parker?
Hey, Sergey. On slide 11, you were showing that basically the measured angle demonstrated a straightening of field lines and that energy was released.
Yep.
I was wondering if you've quantified, how much energy is released in this region from the magnetic field.
I have not done it, but we can discuss it later.
Okay, cool. And then really quick, do you notice any local magnetic pileup in the pickup regions from pickup?
Magnetic pileup from the pickup regions. So the magnetic pileup will be visible in the total magnetic field magnitude.
Right. Does that increase or change in these regions?
So if you want to study the pileup, then you need to do it case by case analysis. Yeah, because when we're looking at the case studies like this one, we're not looking at the structure from the day side to night side, but we're crossing it in perpendicular direction. So it's really difficult to look into the behavior of magnetic field from the day side to night side. So it's an interesting thing to look at, but I don't. Right now, I cannot come up with a methodology to study it, but we can talk about it later. It's just, it's not an easy topic, as it sounds for me.
Okay, great. Thank you.
Okay.
Robin?
I said again, nice talk. And I really liked the way that you illustrate the formation of waves along the boundaries. And you were talking a little bit about how those waves, they propagate into the ionosphere and they enhance the reservoir for escape. And so there's, as you're probably aware, there's a number of us on the MAVEN team that are interested in the relationship between the escape rate and the supply side or the reservoir. Do you have any thoughts on how we could relate the effects of these boundary waves to the amount of supply available for escape and maybe also the effects on escape directly?
So in order to quantify the related ion escape, I think we need to just select a subset of data close to periapsis and look at the densities of the heated ionospheric population. This can be done. It can be like a separate paper. Yeah, and that might be a good idea. So I think, we can just select the subset of population which is heated and quantify it. Yeah, that's something that can be absolutely done.
All right, thank you.
Thanks.
Anyone else online? Don't see that. any new questions from the room? Then I would say thank you for a great talk,
Thanks
Sergey.
for listening.
Thank you, everyone who joined over the Zoom.